Yo, what's up guys, and today we're going to be talking about the new additions to my Minecraft CPU. And so first of all, we're going to talk about my ALU, which has 8 operations and 3 flags. Now first things first, let's talk about how I input numbers into my ALU. So because it can only take one number in at a time, and usually operations require 2 numbers, I made a temporary register, which you can see every operation has a temporary register. And this is basically just a mini memory cell that can hold my first input so that I can enter my second input and get my answer. So let's try it out. So maybe I input 101, which is the binary number for 5. I can unlock this and lock it again, and so that saves my 5 to the temporary register. You guys can see it right here. Now I can enter another number, maybe 311, and I should get 8. 1000, and that is because my ALU is set to addition. Now how can I set it to something else? The setting function is very simple. It's just a 3 to 8 decoder, and there is just a little register at the beginning. So maybe I want to set it to subtraction, which is 1, so I unlock that and lock it, and now subtraction is saved. And so we see it's decoded here into subtraction. And so then that unlocks this torch over here, which allows the subtraction output to be outputted. So right here we have 1, 0, which is 2, which is 5 minus 3. And I can set this to anything else I want. I mean, here we have subtraction, we have addition, we have ORing, we have ANDing, we have XORing, and we also have single operand operations like NOTing, bit shift right, and bit shift left. Now let's briefly talk about the flags. Right here I have the carry flag, I have the 0 flag, and I have the A is greater than B flag. So let me explain what these mean. The carry is probably the easiest flag here. It turns on when a sum is greater than the ALU can handle. So the ALU is 8-bit, so whenever two numbers added together is a 9-bit number, that carry flag will turn on. The 0 flag is another easy flag. It's really just when the output is 0, and I'll explain why this is useful in a little bit. Now, the A is greater than B. This is a conditional flag. And so with my last ALU, instead of having flags like this, I had 4 other functions attached to this. I had equal to, not equal to, greater than, and less than. And so I made my own mechanisms for these, but it's actually much easier than I thought. So I actually can use the subtractor to compute all of those conditional operations. The first one is equal to. By simply subtracting the two numbers that I want to compare, the 0 flag will turn on if they're equal, because anything minus itself is 0. The A is less than B is actually really simple too. If the A input, which is knotted, is less than the B input, which is not knotted, it will actually have a carry. The subtractor will have a carry value. And so that carry simply just goes down to the A is less than B, and it turns on. And with a combination of the 0 flag or equal flag and the less than flag, and using any sort of inversion flag, I can make any logical comparison I want. I can do equal to, not equal to, less than, greater than or equal, less than or equal. Now that we talked about my ALU, let's talk about my program memory. So this is my program memory. It has 256 instructions, each instruction containing 16 bits or 2 bytes. But it is much more compact than my previous designs, and I'm going to show you why. This is how I would originally store instruction steps, where I have a redstone block for a 1 and a space for 0. And so the signal has to travel through a comparator to go to the output, and I can lock that comparator. So whenever I unlock it, if I go down here, I can turn off the redstone signal, and it will allow whatever I have saved in the redstone blocks to be outputted. So this design I found on a Matt Batwings video, so I suggest you check that out. I'll leave the link for the video in the description. But this uses a single redstone tower, and it is only 1 block wide. As you can see here, this is actually 2 blocks wide, and notice it's much shorter. And so how this works is by putting a repeater where I want a 1 to be and leaving nothing where I want a 0 to be. And so by powering this redstone line, the signal can travel through the repeater and become a 1, or there's no signal traveling through and it becomes a 0. This is a much more efficient and compact way to store ROM in a program memory. Now for the decoder. It looks a little weird because it has 6 bits here and then 2 bits down here, but let me explain. This works just like any other 8-bit decoder, but it is made specifically to reduce lag. And so how it reduces lag is that the memory is broken up into 4 major units of 64 instruction steps. And so these 2 bits down here, which are actually the top 2 bits of an 8-bit memory address, these tell which unit I'm working with. And then these 6 bits are just for which instruction step out of the 64 is being outputted. This reduces lag because the signal only has to go through 64 instruction steps instead of 256, because it only has to go through 1 memory unit. So let me briefly explain how I code this. So I use a MC schematic library in Python, and it can basically create a world edit schematic that you can paste in. So I used some modified code from Matt Batwing's GitHub repository, and I'll link that in the description also. And so I just modified it to fit this design. And so then it can take a file of zeros and ones and turn it into a Minecraft schematic that I can paste in using world edit. Then I also added a compiler that can take my own assembly language and convert it to binary. I'm not going to show it in this video, but it will definitely come up in the future. So with all these additions I showed you, I can soon show you my CPU. But first I'm going to make a video on a new and larger screen I developed for my CPU. So stay tuned for that, but that's all for now. Peace.